Hi, in this video I would like to briefly comment on some basic points behind the wave equation in one-dimensional, particularly for waves on strings. Here we have a quick definition what would be wave for us. So wave here is a signal, a disturbance that is transmitted from a point to other in space and time with definite speed. I stress here the definite speed, so here we have our definite speed to be c. I stress definite speed because if it doesn't have a definite speed, for example, a line would obey this equation, but we would not like to tell that a line is a wave. So physically, we ask this equation to follow definite speed. And at the moment, I'll just say that's a hyperbolic equation, but in a minute, I will come to that. So we also can classify these waves in generally as longitudinal or transversal. The longitudinal waves, they are waves where the perturbation travels in the same direction as the propagation. So both the wave and the disturbance will travel along the same line. In this case, we have, for example, sound waves or pressure waves, also called P waves. In the case of transversal, we have the perturbation is orthogonal to the direction of propagation of the wave. And that's the case, for example, of Maxwell's electromagnetism and waves on strings. And here we are talking about waves on strings. So, talking about waves on strings, which is just mentioned, transversal waves, we have here one-dimensional wave equation. And this one-dimensional wave equation, as you can see, it has it depends on x, position, and time, and it can looks like we have a two-dimensional object, but that's not the case. The thing is that this phi here, in the case of waves on strings, we are talking about a function which we will say how much each point of the function will go up and down. So in that sense, it's accessing other dimension, but it's just that the object, in our case the string, is embedded in a two-dimensional space. So for example, it's like if we have a function like f of x is equal to x squared, we know it's a one-dimensional function, but you can still plot it in two dimensions, where y will be our vertical coordinate. So here it's one-dimensional, and phi says how much each point of the curve goes up and down. And then we have c, where the speed of the wave could be v, but in this case we are adopting c, and it's square root of t over whole, where t here is the tension along the string, and whole is the linear density of the material of the string. Both of them depends on the material and on the string itself. This is a Cauchy, we call this a Cauchy problem, and basically we have here our differential equation, and we also have two pieces of information. One is our initial position, so phi we will call the position of each point of the string, and when you set time is equal to 0, this is our initial position. So we can also call this by that, or even that. You can also see that this as well in the literature, where this 0 indicates time 0. But then we can also call this a function f of x, because this is a function of x of space, so we can just call this f of x. So for each point of the string we have an initial position, so that's a function, not a number. The same goes for the velocity. Where the velocity here, we need to be careful because we have two velocities here. One is the velocity of propagation of the wave, and the other one is d phi dt, so it gives a velocity of the perturbation phi, which in this case is going up and down. And when you set, we take the derivative and set time is equal to 0. So we first take the derivative and then set time is equal to 0. This can be written like this, or can also be called a function, namely g of x, because for each point of the string we have a different initial velocity. So we have different initial velocity and different initial positions. And that's what we call a Cauchy problem. I would like to highlight that we have some assumptions to get to this equation of wave equation strings, and the first one is that we are using a small angle approximation, that the amplitude of the wave is small compared to the wavelength, and that's translating the sine of theta, where theta is this angle between horizontal and the force, in case the tension is the sine is proportional, is equal, almost equal to the tangent of theta of the same order. So that's very well known. And also sometimes it's not said, but it's implying that the tension is constant along all the string as well. And also the whole should be constant, because if a whole is not constant, in the case of our string, we would have a term like a derivative with respect to x. So here is derivative with respect to x involving the velocity itself, because the velocity would change from point to point. In that case, the velocity would need to receive the derivative. So in that case, we would have something here where this derivative here also includes the c itself. So the c would not be free of the derivative. So these are some assumptions I would like to mind, and we can generalize. So generalizations, we have many ways of generalizing the wave equation, and the most obvious one, of course, is to increase the dimensions. So if we go to more dimensions, for example, here we have 3 dimensions, spatial dimension, here one time, then we are already in some sense generalizing it for more dimensions. You can see that the sign is kept negative for the spatial ones, or can be negative, of course, to the time, and positive for the other ones. You just need to multiply by -1. But this minus is important for hyperbolic, and I will come to it soon. Now, another option is if we, instead of string, we consider fluids and solids, for example. So what would change? Basically, we would have to change our speed of propagation of the wave, which is different from the other speed you just talked about. And instead of tension of the string, we would probably have to use Book modulus, the Book modulus, or the shear modulus, or Young modulus. Where for fluids, for example, for the sound, we would use the Book modulus. And for solids, crystals and solids, we would have to use these other two, for example. So basically, this is how the changing the medium from string to a solid or a fluid would change our velocity. Another one, we can also consider taking into account more effects. So here is our basic wave equation, one-dimensional, but if we allow for other effects to come to be in account, for example, we can also allow an external force, could be the gravity, for example, of the string. We could also allow a restoring force, which is proportional to the function itself. Here it's the function, so it's proportional to the function. And then there's a restoring, which could be like a spring. And we know that in the case of the spring, in basic physics, force is minus kx. So it's proportional to the displacement. And here is our displacement. We can also have something frictional or damping, which is proportional to this velocity of phi, so phi of t. And all these factors together, we would have something more general. In that case, we'll have what's called telegraphy equation, which is more general wave equation. Also, instead of talking about strong solutions or classical solutions, we could also be talking about weak solutions, which are solutions almost everywhere. But with this requirement of weak solutions, we could make contact with functional analysis, which is a place where a field where the strings in physics make contact with mathematics as well. And for example, just to give an example, basically what we could ask that here, instead of being 0 as required by the wave equation, we could say that it's not 0, but this is delta of x, where delta of x is at 0 almost for all points, right? Apart from one point, namely point x is equal 0. So so for point x is equal to 0, for all points which are not the point 0, the function is 0, but at 0 the function is not 0. So that means it obeys almost everywhere the wave equation, particularly, but one point in particular will not follow exactly the wave equation. And in this case, of course, we have what's called the Dirac delta, but it's just an example. So basically, you would be, instead of talking about C2 functions where we have continuity and two derivatives, the existence of two derivatives, both in time and in space, we would be looking for weak solutions which bring us to the field of distributions or locally integrable functions. So here is how can we make it more general in that sense. And then we come to a simple classification of second order partial linear differential equations, where here we have a differential operator, L, let's call, applied to our function phi, and in general we can have many coefficients A, B, C, D, E, F, and G, where each one comes with second derivatives, mixed derivative here, or just second derivative on time, or just one space, just one time, or proportional to the function itself, and a constant. And our differential operator is L, but what we call the principal part of L is just the part with the second derivatives, namely this one. So here it is. Among all the solutions of the principal part, we have one which is we can call characteristic curves, and they are basically constant solutions of this principal parts. So because it's a solution, that means of course we need to set this equal to 0, and then we look for constant solutions of this equation, and these are the characteristic curves. But in particular, what I would mention is that there is a quantity called the discriminant of our operator, here we call delta, which is b squared minus ac, and the sign of this discriminant will tell us if our equation is what kind of equation we have. So if this delta is positive, we say that our equation is hyperbolic. And a model for hyperbolic is wave equation, which is what we are talking about right now. If this delta instead is 0, then we have a parabolic differential equation, and the model for that is the heat equation. If the delta is less than 0, in that case we have an elliptic differential equation, and a model for that is the Laplace equation. And well, this comes from the details of that. I'm skipping the details of how we come to this, but if you look the reasons why we come to this, if you look at this equation, for example, what it has to do with what we call characteristics, directions of our differential equation, it resembles very much the Bhaskara formula where we use for solving quadratic equations, right? Actually, you could even have here b squared minus 4ac to be exactly equal, but in that case you would not have this 2 here, but I started with a 2 here. But if I didn't start with a 2 here, just without 2, in that case without 2 here, we would have here 4ac. And then we know that if delta, this delta here, it's positive, the square root will give us 2 real solutions, and then we call these 2 characteristic directions. If the delta is 0, we have just one solution, and then it's just one real direction. And instead, if the delta is actually less than 0, we have no real solution, so we say we don't have any real characteristic direction. So because we're talking about, as I just mentioned here, hyperbolic, we are talking about 2 real solutions, 2 real characteristic directions. And for example, you see this in the case when you look at the D'Alembert solution, where we write our solution of our wave equation in terms of 2 directions, where we call forward direction and backward direction. And then you see this in another opportunity. Some quick remarks here. It's that this b squared minus ac, this discriminant, can also depend on the point, so it can change in our domain. So if it's changing our domain, we could have some PDE, partial differential equation, where it's of mixed type. In that case, in some regions it would be, let's say, hyperbolic. In another region it would be elliptical, so it would be our mixed type. This can happen. Also, this classification can be extended to the case of more variables. Here we have just 2 variables we started with, but we can generalize this for more variables as well. However, these are not all the possible. We are not talking about all possibles here. There are other types, for example, the ultra hyperbolic, but this one we only see when you are talking about more variables. Also, for example, Schrödinger equation, which I didn't mention before, does not fit into the above categories. And particularly because when we talk about this classification, we're talking about constant real coefficients. And in this case of the Schrödinger, we would have something here which is I, so it's complex, and we don't have these real characteristics directions, so it does not fit above. Then now we could ask, when well posed this wave equation or differential problems in general, differential equation. Well, this was much later answer, much later than the wave equation itself. So in the 20 years, 1920s, Hadamard condition. So according to Hadamard, we can say that our differential equation, here we are interested in the wave equation, it is a well-posed problem when we have 1, 2, and 3, when 1 is the existence, 2 is uniqueness, and 3 is the solution depends continually on initial conditions. Sometimes this is also called stability. Existence is the most obvious. Uniqueness, well, uniqueness, that's the reason why we have initial and boundary conditions. So generally we have our equation, and we have solutions for it. Existence, 1 is fine, but then we don't have uniqueness, so we need some boundary conditions or initial conditions. So when we can use this initial and boundary condition, we restrict our solutions, and then we get uniqueness. But however, if we use too many boundary conditions, too many initial conditions, we will perhaps lose existence. So there is this game between existence and uniqueness, where the initial and the boundary conditions are the responsible. I just would like to mention something else, which is about the stability or this continuously dependence on the initial conditions. For example, we don't have this in our case. So for example, if we are solving the heat equation, which is first order in time, the heat equation is a parabolic equation according to our classification. And it means, as we just mentioned before, it means that we have one real solution or one real direction of these characteristic directions. And then what it will mean here for us in terms of not following stability is that if you try to solve this equation backwards, for example, backwards here would be the negative direction of time, then we would find that we would not have a well-posed problem, because we would not have this stability. So we can have a solution, an existing solution, and it's stable if we're talking about the positive time direction. However, if we are talking about the negative direction, we cannot say there is a solution, but if there is a solution in the backward direction, it is unstable. So in that sense, the heat equation in the backward direction tell us that we can fail to fulfill our requirement number 3 according to Hadamard well-posedness problem. Then we also should mention that when we have an initial value problem, that's usually when we call this a Cauchy problem. So this is an initial value problem. And we can also have, apart from initial value problem, we can also have the initial value problem with boundary conditions. And then we can exploit this in the case of waves on strings in a later video. But if we have boundary conditions, this initial value problem with boundary conditions can also be called Cauchy problem generally. But however, because we have boundary conditions, we have 3 types of boundary conditions. One is type 1, what we call Dirichlet boundary conditions. In that case, our our boundary conditions are restrictions upon the function itself, in that case phi. And type 2 or normal boundary conditions, they are conditions upon the derivatives of our function phi, derivatives upon this function. And the type 3 is the one which we call robbing or mixed boundary condition. In that case, we have some linear combinations, usually homogeneous and linear, and these will be a mixture of the function and derivative of the functions itself. For now, if you want to follow the next videos, you can consider to subscribe and leave a question or a comment below. Thanks for watching and see you in the next video.